Hey there. Welcome back to Abstract Algebra. I'm in this early stage as we're switching over to this new mode. I'm going to be continually sort of experimenting. So this time I'm going to try just having you hear my voice, not trying to light this room and work on a whiteboard, but I've kind of pre-prepped some notes on this tablet. I'm going to just kind of walk through the notes instead of writing. Well, towards the end, I'll write a little bit, but I think this will kind of speed it up a little bit, and you can kind of pause. And then when we talk online all together, we can kind of talk about how this is going. All right. So purposes of what I want to tell you about. Last time we were looking at this new notion of factor group, and in the top of the slide here, I'm going to remind you how all that stuff worked. But in the purpose of this particular lecture is I want to look at some examples of them. I want to give an idea of what it's like to compute around in a factor group. Okay, so let's start off by looking at this. What is a factor group? This is what we did in the last lesson. So if you have some group G, yeah, and then you have a normal subgroup of it, remember that that's what that notation means. Let me see if I can get a better color for that. You have a normal subgroup of the group G. Yeah, I like that better. Then what's the factor group? Well, it's just the set of cosets. I wrote left here in parentheses because it's a normal subgroup. Left and right cosets are the same. It's the set of cosets with this binary operation. We call it coset multiplication. And that binary operation, you multiply the coset containing A and the coset containing B, you get the coset that contains A times B. When you work in this group, it's important to remember that the subgroup itself is the identity under that multiplication, coset multiplication, and the inverse of a coset is the coset containing the inverse. Great. A couple more things on the recall category here. What does normal subgroup mean? Well, a normal subgroup is a subgroup, first and foremost, that no matter what element in the group you pick, that kind of sandwich, A inverse NA, would always be a subset of N. So for any little n, if you like, if you want to kind of write that out in an element form, this means that you take any little n in N and you multiply it by any A and its inverse in G, and you're always going to get an element of N. So that needs to be true for every N in N, for every A in G. This is another way. It's kind of an element by element way of thinking about what this means. Okay. If G is an abelian group, every subgroup is going to automatically satisfy all this stuff. It's important to know. Keep in mind, so you don't have to work hard to know if something is a normal subgroup in an abelian group. And then our kind of only other result about this stuff was that if you have two cosets, exactly two cosets, you'd always be a normal subgroup, right? Okay, so let's look at some examples. The first one, it's kind of our guiding example. In the first lecture, the whole coset multiplication was motivated by this thing. So we'll just kind of quickly remind ourselves that you take the group of integers, in this case, that's what I'm talking about, is the group of integers. And then I fix some integer n, and I let the n be the set of all of its multiples, right? So we know what's in that set. This nz, if you want to write it in set builder notation, well, you just take your number n, and you multiply it by any integer and gather up all the results. So there's integers equally spaced by n, starting with 0, going positive and negative values. All right, and then so in that case, the set of cosets, well, it's just this group z sub n that we've been working with all along, the group of integers mod n. It is a set of cosets. This is our guiding example in this stuff. In this notation, these brackets around the thing, that's just a shorthand for the coset. The bracket A is just the coset containing A. All right, so a finite cyclic abelian group. It's a group of cosets. All right, let's take a look at the next one. Next example. This is a busy slide, but we'll just kind of walk through it here together. This time I want to take G to be the matrix group, 2 by 2 matrices. And this is a subgroup we talked about in class when we were still meeting face-to-face back in the good old days. The subgroup of matrices is determinants are positive. And we had a nice conversation that's an index 2 subgroup. An index 2 subgroup is normal, okay? So it's a normal subgroup. It's got a factor group. And my question is, well, what is it? What is this factor group? Have we seen it before? Do we quote unquote know it? All right. Well, to make some computations in it, we need the cosets. There's two of them. This is a familiar looking matrix. It has determinant -1, so it's not an n. So it represents the other coset. So we could write that. And I want to kind of give you an example of like, well, when you're doing this, how do you know? If it's a finite example, then you want to know what the group is, you could make a table. You could make a table for its multiplication. If it's a group with n elements, well, then you got to make an n by n table. This one has 2 elements, so it's just 4. And I'm filling this in with coset multiplication. Is it in your mind? I'm talking about this operation right here. When I multiply 2 cosets, I multiply the representatives of them, and then I take the coset that contains it, and I can take any representative of that I want. Okay, so that's what I'm doing. Maybe you've already filled this in down here. So using that definition, n times n, well, that's the coset containing the identity times the identity. Yeah, this is the identity coset. Anything times it is going to be the other thing in these rows and columns. I can take advantage of that. How about this one? The coset containing an times the coset containing an is the last entry in the table. Well, that's the coset containing a squared. So, well, I need to know what a squared is. I don't really need to know what it is because the determinant of a squared is going to be -1 squared. That's 1. So the coset that contains it is this thing. So there's the group table. It looks familiar. It looks familiar. Here's another way. Let's see, that was kind of the Nike method. We just brute forced our way. What about using some of our theory? This group that we're talking about has prime order. It has 2 elements in it. 2 is a prime number. Our Lagrange theorem in the past said that any group with prime order is cyclic. So this group is cyclic. And cyclic groups, you know, are determined up to isomorphism by their size. So a cyclic group of order 2, we've kind of nailed it. This group of matrices, quotiented out by is another way to say it, or this symbol, I'll try to highlight it over again, G mod n, is just isomorphic to Z2. Cool. Okay, let's see if we can do one more. I was thinking about maybe doing 4 examples, but I think I might limit this video to 3, but let's see what you think about this one. All right, so I'm just going to keep using the highlighter to kind of show you what I'm talking about as we go. So this time, my example is complex numbers, non-zero complex numbers. Remember that prime means that. And the subgroup I'm going to take is the unit circle group. And that's a normal subgroup because the complex numbers, I didn't write it on the slide, but I'll write it now. Complex numbers are abelian. Every subgroup of an abelian group is normal, so I can talk about the factor group. This isn't a finite group, so Lagrange's theorem doesn't tell me how many cosets there are. So this is kind of another useful idea. You can always kind of ask yourself this question. The question is, under what conditions do 2 elements of the group represent the same coset? It's always a good idea when you're thinking about a new factor group to ask yourself this question and try to answer it. And let's see how we can try to answer it. So I'm picking a couple of complex numbers. Didn't write it here, but I can. What are these things? Let me sort of squeeze it in over here. Take some W, some Z. They're any 2 non-zero complex numbers. Okay. And then I'm asking, like, well, when are the cosets that contain them the same? Well, the first answer is kind of always the same. It's the definition of cosine inequality. It's when the product of the inverse of one of those things with the other is in the subgroup. And here that subgroup is the set of elements of length 1. And so that means this thing has length 1. Okay, and by properties of absolute value, I can rewrite that. And that's kind of a condition I can finally understand. Z and W represent the same coset when they're the same distance away from the origin. They're equidistant from the origin. They lie on the same circle. Talking about circles, let's draw a picture. Sorry, I'm trying not to reveal too much here. The punchline. But yeah, here's my crude picture. Drawn the complex plane, the unit circle there, drawn in white. I've marked the number 1 to kind of try to indicate that that's a unit circle. And then I've picked an arbitrary complex number z up there in the first quadrant. And what I drew is a rough sketch of the set of points that are the same distance away from the origin that z is. That's what that's supposed to be a picture of, is if you imagine this length as a radius of a circle, it's the radius of length z. That red circle I tried to draw was the set of points that have the same length. All right. So this set of cosets, I know what it is. It's just a set of concentric circles centered at the origin. There's exactly one of those cosets for every positive real number. I highlighted the positive real axis in the green in the picture there, and what I'm saying is that every single coset has exactly one representative on that green ray. So the set of cosets is kind of in correspondence with the set of points in that green ray. And not only that, the way we multiply cosets, we just multiply the representatives. So if you picked points in the green ray, let me just draw a couple of them here. If I picked a couple of real numbers, I'm going to make them have, oops, didn't want to do that. Maybe this one, I'll call it alpha. It's a real number. Maybe I'll call this one beta. Yeah. So the cosets that they represent are circles. I won't try to draw the whole things, but any number on that circle represents the coset. Any number on that circle represents the coset. And the way I would multiply the cosets containing alpha and beta is I would just take the coset containing alpha times beta. Well, alpha times beta is also going to be some real number. Yeah. So why bother dragging all these cosets around? I kind of feel like I know what this group is. It seems like we could just work with the positive real numbers. So I don't have a proof of this here today, but I'm kind of alluding to one of our next topics, the section in 2.7. We'll get a tool to prove what I'm kind of just going to leave as a conjecture right here. So I wrote seems like, but it seems like this factor group, this set of cosets, it seems like it's just the positive real numbers. Okay, so we need some more tools to prove that, but hopefully that kind of conversation gave you an example of how you can kind of think about some of these things. You know, what does it mean to try to understand what a factor group is? Well, you're trying to understand the answer to the question, under what conditions do two elements of the group represent the same coset? Cool. Okay. Well, this video is getting a little long. I'm going to cut it short. I'm going to do one more example. Maybe I'll tease you with it and you can kind of ask me about it in class on Zoom sometime. But the group I was going to take to be the same, non-zero complex numbers. But this time I was going to switch the roles around and sort of take n to be the positive real numbers, not the unit circle. It's also a normal subgroup. This thing's abelian. Don't have to worry. So I've got a factor group. It's the complex numbers. And maybe you, on your own, could ask yourself some questions like, under what conditions are two cosets equal? Yeah, maybe we'll see if we can answer it together in class. Okay, so I'm going to cut that here. Thanks for listening, and let me know if you have any questions.